So this talk is about maximum bipartite matching in roughly n squared time via a combinatorial algorithm, and this is joint work with Sanjeev Khanna. In the bipartite matching problem, we are given a bipartite graph, and our goal is to compute a matching of maximum cardinality in this graph, for example, this matching. And as you probably know, one way to solve this problem is to cast it as an instance of maximum ST flow. So we build a directed flow network like this. We set the capacity of every edge to be 1, and then solving maximum flow in this network and solving maximum matching in the original graph is essentially the same problem. And so we can use any of the known algorithms for solving maximum flow in order to solve bipartite matching. For example, the famous algorithm of Ford and Fulkerson, what it does, it augments the matching 1 by 1, iteration by iteration, and it has running time of mn. And later, Hopcroft and Karp noticed that this algorithm can be sped up by doing these augmentations in bulk. So the running time of their algorithm is of m square root n. And this is where things stood for a very long time, except that it was noticed that one can also use fast matrix multiplication in order to solve this problem. And then one can get algorithms that are a little bit faster for a special case where the graph is very dense. And more recently, a new paradigm emerged that really revolutionized this whole field. And this paradigm is the use of continuous techniques in order to solve flow and related problems. And this has led to a really long line of spectacular results that recently culminated with this almost linear time algorithm for directed maximum ST flow, in fact, even for the more general min cost flow. And obviously, these algorithms also get the same running time for bipartite matching. So what is common to all of these algorithms is that all of them rely on continuous techniques, and in particular on interior point methods for solving linear programs. So we can summarize the state of the art up to this point like this. If we use continuous techniques, then we can get algorithms whose running time is almost linear. But if we stick to old school combinatorial techniques, then the best algorithm is this really old algorithm of Hopcroft and Karp, whose running time m square root n, except that in very dense graphs, you can get a little faster algorithms by fast matrix multiplication. So this naturally raises the question, is this use of continuous techniques necessary in order to get fast algorithms? Or can we get faster combinatorial algorithms by using combinatorial techniques? So let me say just a few words why we would be interested in combinatorial techniques when we already have such good continuous algorithms. So first, the combinatorial algorithms, they tend to be more transparent and intuitive. Second, there are some really important problems, such as, for example, maximum matching in general graphs, for which we currently don't have candidate continuous algorithms. So to make progress on this problem, it feels like we should get stronger combinatorial techniques. And lastly, algorithms for max flow and matching, they're really important, and they need to be used in all kinds of settings, such as dynamic, online, distributed, and so on. And it is often the case that combinatorial techniques fit in naturally and can be adapted naturally to these settings. And sometimes it's not the case with continuous techniques. So with this motivation in mind, we ask again this question, can we obtain faster combinatorial algorithms for bipartite matching problem? So the answer is yes. And the first, we showed it first in this paper that just appeared in SODA together with Sanjeev Khanna again. And in this paper, we designed a deterministic combinatorial algorithm for this problem with running time m to the 1/3 and to the 5/3. And this already beats Hopcroft-Karp and matrix multiplication-based algorithms on graphs that are moderately dense. And the paper that I'm going to present today, it's a randomized algorithm. It also uses only combinatorial techniques. The running time is close to n squared. So for dense graphs, it's close to the best one can hope for. But for sparse graphs, there is still room for improvement. And using a well-known reduction, this completely automatically also gives an algorithm for maximum ST flow in directed graphs with unit vertex capacities with exactly the same running time. So now I'm going to say a few words at a very high level how this algorithm from our SODA paper works. And then I'm going to say how we improve it in this new STOC paper. So first of all, I'm going to define a problem that's called route and cut problem. And intuitively, this problem, you can think about this as equivalent to approximate max ST flow with unit vertex capacities in directed graphs. And as such, this problem is essentially also equivalent to bipartite matching. It's just going to be more convenient for us to work with it. So what is this route and cut problem? So we are given a directed graph, and we are given two sets, A and B, of its vertices. And we want to route vertices of A to vertices of B. And we also given some target parameter delta. And so what we need to do, we need to compute a collection of paths that connect vertices of A to vertices of B. And these paths have to be completely disjoint. If we manage to compute close to delta such paths, then we are happy. If not, then we want to produce some certificate that such a collection of paths does not exist. And naturally, such a certificate is going to be a vertex cut that separates many vertices of A from many vertices of B, and the separator size itself needs to be small. So this is the definition of a problem. And again, just looking at it, it's morally equivalent to approximate max ST flow in directed graphs with unit vertex capacities. And as such, it's just equivalent to bipartite matching. So now I'm going to focus on this problem only. So now at a very high level, how does this soda paper algorithm works? So it uses really standard techniques such as multiplicative weight update in order to reduce this route and cut problem to a special case of decremental single circuitous path in directed graphs. Now, the problem is that when the graph is directed, we don't really have good, fast algorithms for single circuitous paths. So this is the best previous algorithm, and if we just plug it in, we're not going to get any speed up over Hopcroft-Karp. So the second sort of insight or part of the soda paper is that we only need to deal with a special case of single circuitous path that arises from this reduction. And for this special case, we can simply speed up this algorithm and get it faster. So this is at a very high level how the soda paper algorithm works. Now I want to tell you a little bit more detail about this algorithm of Bernstein, Gutenberg, and Saranurag for decremental single circuitous path in directed graphs. So this algorithm can be thought of as having two parts. The first part, we have this input graph that undergoes edge deletions. And so the first part is maintaining expander decomposition of this graph. So a partition of this graph into expander-like pieces. And this decomposition has a property that if we contract these expander pieces, what we get is a graph that's almost like a DAG, directed acyclic graph. And then the second part of their algorithm is just using a known algorithm from before in order to solve single circuitous path on the resulting almost DAG. So this is how this decremental single circuitous path algorithm works. So in our soda paper, one of our main observations is that the instances of single circuitous paths that we get from our reduction from bipartite matching problem, for those instances, we can speed up the second part really significantly. And this is what really gives us the edge. And as for the first part, we speed it up a bit. And this is enough to give us this edge over Hopcroft-Karp algorithm, but not enough to get all the way to n² running time. And as is often the case, this algorithm for maintaining expander decomposition basically boils down to an algorithm that maintains a single expander-like cluster. So we call the corresponding problem maintain expander problem, and its purpose is simply to maintain a single cluster in this decomposition. So at a very high level, if we want to really summarize the soda paper, then we can think about it like this. We can think about it as a reduction from the route and cut problem to maintain expander problem by using all of these technical tools that I mentioned. And so if we want to get a faster algorithm for bipartite matching, generally what we want is a faster algorithm for maintain expander. It's a little bit of oversimplification, but that's what I'm going to focus on. So now let me tell you about this maintain expander problem. So we start with a directed graph and some distance parameter d, and this graph undergoes online sequence of edge deletions. And then from time to time, we get queries. A query is just a pair of vertices x and y. And in response to this query, we need to return a path connecting x to y in this graph, whose length is at most d. and the time to respond to the query should be proportional to the number of edges on this path. And obviously, such a path may not exist, for example, if the diameter of this graph G becomes too large. So to avoid the situation, at any time, our algorithm is allowed to produce a roughly 1/d sparse cut. It should be a vertex cut in this case. And then when this happens, then the smaller side of the cut, A or B, is deleted from the graph. And the separator S is also deleted from the graph. And then the algorithm needs to continue with what is left from this graph. In this case, it's B. Now, if you look at this problem, and let's denote by phi 1/d, then again, at a very high intuitive level, what this problem says is that we have this decremental graph, and we want to maintain it as an expander, as a phi expander. And the only action that we're allowed to do is cutting off sparse cuts from this graph. And then we also need to support some short path queries. So this kind of problem, it arises a lot in many settings, and it was studied a lot, mostly in undirected graphs, but also this previous work of Bernstein, Gutenberg, and Saran-Wrach studied it in directed graphs, and they get an algorithm for this problem whose running time is roughly m/phi², which for us is md². So this is okay for many settings, but unfortunately for our case, for our problem, this d can be very large. It can be as large as polynomial in n, so this running time is just too slow. And in our SODA paper, for the special case, again, that arises from the reduction, and for some very specific setting of parameters, we got an algorithm whose running time is md plus n², and this was enough to get what we got, the result in the SODA paper. And I just want to say that it just uses completely standard techniques, such as cut matching game and Evans-Shiloh tree. But this is not enough to get n² time that we want to get for the STOC paper. So now let me tell you how does our result in STOC paper look like and how it speeds up this algorithm. So our main sort of technical contribution is to show that we can reduce this maintain expander problem to route and cut. So if you remember, in route and cut problem, we have these two sets A and B of vertices, and we want to connect A to B with many disjoint paths. So what we showed is that if we have an algorithm for route and cut, which is quite fast, the running time should be roughly n times n minus cardinality of B. Then we can get algorithm for maintain expander whose running time is close to n². So if you look at this, so if this set B of vertices contains a lot of vertices of the graph, almost all the vertices, then the algorithm becomes quite fast. And in fact, it may even be faster than the time that is needed to read all the edges in the graph. And this is necessary for our reduction. So this reduction is non-trivial, but I don't have time to go into it. So to summarize, what we show is that if we get this very efficient algorithm for route and cut, then we get an algorithm for maintain expander with time roughly n². And then the reduction in the other direction, it follows from, again, the same techniques as before, multiplicative weight update and single associative sparse on almost DAGs. But now, because we need to be very careful and we need to get this super efficient running time for route and cut, the second reduction also becomes quite challenging. But what we see so far, it looks like it's completely useless because we have two problems that we want to solve. And all we show is that if we can solve one of them efficiently, then we can solve the other one efficiently. This is not helpful. So to get out of this problem, what we do is we parameterize both problems with a new parameter R. So if we look at the maintained expander problem, for example, this problem already comes with a distance parameter D. And we say that an instance is R restricted if this D is at most 2 to the power of R² log n. If you look at the route and cut problem, if we can manage to run delta disjoint paths from A to B, then it's easy to see that most of the paths, they're not too long. Their length is at most roughly n/delta. So we'll think of this n/delta as our distance parameter, and we'll say that this instance is R restricted if this n/delta is at most 2 to the power of R² log n. So our reductions, they're a little bit more careful. So we show that if we can get fast algorithm for R restricted route and cut, then we get a fast algorithm for R restricted maintain expander. And in the other direction, we go from our restricted maintain expander to R+1 restricted route and cut. When R is equal to 1, then it's very easy to get a fast algorithm for one restricted route and cut. And then we just use induction on R to get fast algorithms for both of these problems for the whole range of the parameters. And I want to make just a few more final remarks about our results. So first of all, if we look at these previous papers, the first paper is on decremental single-source shortest path, and the second is also the paper for bipartite matching. Both of these papers use maintain expander problem, maybe implicitly, but in both of these papers, this problem was only defined for graphs that are unweighted, in which all edge lengths are unit. However, both of these papers need to use this problem on graphs that do come with edge lengths. And this is one of the major sources of inefficiency of both of these algorithms. So in our paper, what we did is we generalized the maintain expander problem so that it also works with arbitrary edge lengths, and we also provided an algorithm for it. And one last remark is about edge deletions and edge length increases. So there is a standard method for solving flow problems that we also use, where first we use multiplicative weight update to reduce the flow problem to single source shortest path on graphs that undergo edge length increases. And then you can reduce this to single source shortest path on graphs that undergo edge deletions. So ultimately, people usually work with single source shortest path on decremental graphs that undergo edge deletions. So what we observe in our paper is that actually working directly with edge length increases may be more efficient. And this is also something that allows us to speed up our algorithm. So let me give you a very quick motivation. And it's a standard trick that is used a lot and that we also use in our paper. So suppose we take some graph and we want to embed, let's say, some expander into it. So we map the vertices of the expander into the graph. We will map its edges into paths in this graph. And let's say that all of these embedding paths are short and they cause low congestion. So now suppose we delete some edge from this graph G. So generally what happens is that every edge of the expander X whose embedding path uses this edge also needs to be deleted. So the deletion of some edges in G can lead to quite a few deletions in the expander X as well. But now let's see what happens if we just take this edge E and we simply increase its length a little bit. And now if we look at some edge of X whose embedding path uses E, well, we maybe don't need to delete this edge immediately because all that happens is that its embedding path, its length grew a little bit, but not too much. We could wait until the length of the embedding path becomes way too high and only then delete it. And when you work with multiplicative weight update, then generally these edge length increases, they happen in a very controlled way. They don't go crazy. And because of this, if you work directly with edge length increases, it can actually help you because, for example, various embeddings, you can keep them for longer and they're not destroyed as often. So to summarize, we obtain a combinatorial randomized algorithm for bipartite matching and also for maximum flow in directed graphs with unit vertex capacities. And the running time of the algorithm is close to n squared. And at a high level, a few technical highlights, we show that route and cut problem and maintain expander are sort of equivalent. They reduce to each other. And then we use parameterization to solve both of them recursively. We generalize the maintain expander problem to arbitrary edge lengths. And also we notice that working with edge lengths increases directly instead of edge deletions can help. And open problems, the most obvious open problem is we would like to improve the running time of our algorithm to almost linear. Second, and this is a question that I had on my list, is can we get fast combinatorial algorithms for maximum flow with general edge capacities? But I just learned that actually there is a really a new result that just came out, which is a combinatorial algorithm for maximum flow whose running time is close to n squared. So now we can move the goalpost on this and ask, can we do the same for min cost flow? And lastly, can we build on these techniques to break the long-standing m squared and running time for general matching? And that's all. Thank you.